Good morning, everybody. Today we'll be looking at the last chapter of particle and nuclear physics. We'll be looking at fission and fusion, and we'll also be looking at this in terms of the fusion processes that are going on inside stars. Click on that. Right, so we'll be looking at fission and how this is handled in nuclear reactors. We'll be looking at fusion as well, in particular linking this to nucleosynthesis, so how hydrogen, helium and lithium, etc. were made in the early universe, and also linking this to the solar neutrino problem. So let's have a look at fission and fusion. What are they? Let's go back to our plots of the binding energy per nucleon that we had for the number of nucleons that we have in a nucleus. And you remember there was this broad maximum at roughly 60 nucleons that happens around iron. It's a very stable nucleus. Now what we have here is fission is more probable to the right of this, i.e. they're trying to get down, split up into smaller nuclei to get to a higher binding energy per nucleon. And then to the left here, fusion is more common as the smaller nuclei bind together to get to larger nuclei, which have a larger binding energy per nucleon. So it's really trying to maximize this binding energy. That's the important thing here. So how do we try and understand this? So we're going to understand this in terms of the semi-empirical mass formula. If you remember there, we have our volume term and surface term and Coulomb term, etc. here. Now, when the volume, of course, if they split or they merge, doesn't change. The volume will just be the addition or of the two pieces. And it's really about how the Coulomb term and the surface term change in the semi-empirical mass formula. So when we have a look at fusion, we've got two very light nuclei, and their surface term is actually pretty large for their volume. They've got a large surface to volume ratio here. And when they fuse together, their surface to volume ratio changes. It decreases. So we're really decreasing the surface term to the volume here. It's the surface term that's really important. Now, when we have more nucleons, more protons in particular, this term, our Coulomb term, is going to increase. So we're going to have a decreased surface term and an increased Coulomb term when we fuse two light nuclei together. But that's okay. What we'll find is that the difference in these still gives us a larger binding energy per nucleon, i.e. that drop in the surface term is larger than that that drop in the surface term is larger than that increase in the Coulomb term. Let's have a look at fission then. It's really the other way around. We've got a very large nucleus here, and the Coulomb term is very large. We've got lots of protons in there, and the repulsion is actually quite large. And by splitting into two, the Coulomb term is decreased, but the surface energy, that term does increase as well. But the effect is smaller, and overall, the binding energy per nucleon is larger. So we have a preference to go towards this broad maximum at roughly 60. Large nuclei will do this by undergoing fission, and the light nuclei will do this by fusing together. Now, whether we have, well, we'll start concentrating on fission, and then we'll go to fusion in this lecture. Let's start with fission. So a nucleus will undergo fission spontaneously if the energy released is larger than zero. And so we're going to need to take into account the binding energy of the two daughter nuclei and the binding energy of that large initial nucleus. So let's have a look. When can we actually expect this to be larger than zero? We're going to sort of start with this toy model where we have a nucleus with a number of nucleons and z number of protons, and it's going to split into two nuclei. with A1 or A2 and Z1 and Z2 number of nucleons and protons there. Now, it depends how they split. How is this going to split? The first nucleus is going to take some proportion of the nucleons. Let's call this Y, and let's assume that it takes the same proportion of protons. I mean, this is what we see. The ratio of protons to neutrons in these daughter particles is usually the same as the parent particle. There's no reason, for example, to assume that all of the protons go to one nucleus and all of the neutrons go to the other. They have the same composition. So nucleus 1 here is going to take Y fraction of the nucleons, and this second one here is going to take 1 minus Y fraction of the nucleons. So let's plug this into the semi-empirical mass formula for this energy released. We've got the binding energy of the first nucleus here and the binding energy of the second nucleus. And what we've got to do is have a look at the change in the surface and the Coulomb terms. And these changes have got to be sum up to something larger than zero for this to happen spontaneously. So we need to have a look at the sum of the daughter particles here. So this is the daughter 1 and this is daughter 2, and then of course our initial one is going to have a total number of nucleons of this Y fraction of 1, and we need to do the same with the Coulomb term. So we're going to plug in this change, see how our surface and our Coulomb terms change for the initial state particle and the difference with those two final state particles. So the maximum energy released, we can have a look at the maximum energy released here for this E0, and we'll just differentiate it according to Y and set that to 0, and that'll let us find the maximum. And we can find that that happens for when Y is a half, so that these daughter particles are equal size. Half of the nucleons are going to each, half of the protons are going to each. So if we have symmetric fission, a large nucleus dividing into two equal parts, the largest amount of energy is going to be released. So let's take uranium-238 here. The energy released when that undergoes fission is 200 MeV, and that's huge, actually. That's just one nucleus. Undergoing fission, 200 MeV of energy is released. And that's 1,000,000 times larger than any chemical reaction that we can have with uranium or hydrogen or anything like that. Now, there's a problem with symmetric fission, and I'll try and show you this. It's to do with this fission barrier here. So I've got this little cartoon of our initial state nucleus, and let's say that the two daughter nuclei form and then they start to separate. The problem is once they've formed and they start to separate, their surface energy increases, but their Coulomb energy does not drop yet. So overall, the potential there is increasing until they actually separate this scission point. So we're going to get increase in the potential from them starting to separate, their surface energy increasing, and then a sudden drop off as they actually separate this scission point. And they'll separate and the Coulomb repulsion will decrease. So overall, we've got a drop in potential and i.e. an increase in overall binding energy when we've split them up. But we have to get over this fission barrier, and that's caused by that surface area increasing before the Coulomb term drops. And this is a very simple tunneling problem. Again, tunneling is going to come in quite a lot with the nuclear part of the course. What we need is to tunnel through this fission barrier. Now, it depends on how much energy we need here. Traditionally, we'd need a sort of 6 MeV for uranium-236 to get over this barrier, or we're going to have to wait for the tunnel through. Now, it's quite interesting that the energy released is largest. We saw it was maximal when we have symmetric fission, but the problem is, so is the Coulomb barrier. This Coulomb barrier here for fission is largest for when we have symmetric fission. If we have asymmetric fission, this will drop. The energy released will be lower, of course, but it will still be non-zero. So in fact, asymmetric fission is more normal. because this barrier is smaller and easier to tunnel through or easier to gain energy to get over that barrier. So symmetric fission gives you the largest energy released, but because of this fission barrier, it's actually not the norm. Now let's have a look at this fission barrier in detail. What's happening? We're basically deforming our nucleus before it undergoes some scission, the scission point, and actually separates. So we're going to take our typical sphere and we're going to deform it into an ellipsoid. And this will give us a changing binding energy because of the surface term, and also in part because of the Coulomb term, because it will be different across your nucleus. So we'll take our A and B axes and deform them by a small amount, epsilon here, and we can plug this into our surface term and our Coulomb term to see how each one of those changes, add them up to have a look at the change in binding energy. So what we find is that the binding energy is going to be larger than zero. Once this change in binding energy becomes larger than zero, we are going to have fission. This nucleus is basically going to become unstable because of that deformation, and it will undergo scission and split. When does this happen? So if we have a look at this, this is going to happen when z squared over a, we can have a look at this binding energy. When this is larger than zero is when z squared over a is bigger than this term here for the coefficients of the surface over the coefficient of the Coulomb term, and double that. And this is going to happen because these are just constants here when this is larger than 47. So this is telling us that when we have z squared over a larger than 47, our fission barrier should actually vanish, i.e. this change, we deform the nucleus just a tiny bit and it will become unstable and undergo fission. So for large z squared over a or 47, our fission barrier should vanish. Let's go and have a look. Is that true? So let's plot z squared over a here. We can do this for thorium, uranium, plutonium, etc., all the way cadmium. And we find we can plot their lifetime, and it's very large for the low z squared over a, on the sort of 10 to the 20 years here. So it's taking a very long time, and that's because it has to tunnel through a very high Coulomb barrier. But our lifetimes dramatically drop. This is a log scale here. Dramatically drop to sort of 10 to the minus 8 years here for z squared over a of 41. So that means that our fission barrier is much lower, and it's easier to tunnel through, and that's why the lifetime for fission is much shorter. So we can have a look at this in a slightly different way. This is our fission barrier here, and we've got a z squared over a here of 16, 100 nucleons there, and a z squared over a of 16, and we've got quite a high fission barrier to overcome there. I mean, the energy released is quite low, but we've got quite a high fission barrier there. As we get to z squared over a of around 36 here, the fission barrier has decreased, and that's when the lifetime also starts to decrease. It's much easier to tunnel through this barrier. And then as we get closer and closer to that magic number of sort of 47, the fission barrier pretty much decreases. So the tunneling probability, of course, depends on the height of this barrier. The tunneling probability is low here if our fission barrier is high. It is also low if we go and remember alpha decay. And we had a look at the gamma factor and the probability for the alpha decay to happen. We calculated that the probability for alpha decay to happen was proportional to the exponential of minus 2g. This was our gamma factor. And this gamma factor was proportional to the square root of the mass of the fragment. So the probability for tunneling, if you just sort of consider fission as a bit like alpha decay, right? You've got two nuclei forming inside of a main nucleus, and they're going to separate, or one's going to escape. It's just like alpha decay. So if we have symmetric fission and we have a large mass that is escaping, the probability for tunneling through that fission barrier is going to be low. Whereas if we have quite a light fragment, the tunneling is going to be the tunneling probability is going to be quite high. So large masses mean a low probability for tunneling. So that suppresses again our symmetric fission. Um, and it also means that the mass of the fragment has got to be light. So let's consider fission and alpha decay as sort of two very similar things, and take uranium-238. Uranium-238 here can undergo fission. It needs a little bit of energy to do so, but it can tunnel through that fission barrier with quite a long lifetime. As we saw here, uranium-238 is sitting with a lifetime of around 10 to the 16 years. It's absolutely huge for fission. But alpha decay has not got anywhere near the kind of lifetime. In fact, alpha decay for uranium-238 has a much shorter lifetime. It's far more probable for it to tunnel through a smaller fission, tunnel through because it's a lighter fragment. So alpha decay is sort of like this extreme of fission where just a small part of the nucleus is fissioning off and separating. So we do have quite a few naturally fissile materials. We'll talk about them today, but they tend to be a rare decay because the mass of the fragment essentially suppresses the probability for that to happen, and they're more likely to undergo other nuclear decays. But we can help that along. We can use neutrons to create excited states that will overcome the fission barrier. We can use neutrons to do this. And this is going to be important, you'll see, for the design of nuclear reactors. Right, if we have, I'll show you this, if we have very low energy neutrons, they are really easily absorbed by nuclei. They don't have to overcome any Coulomb barrier, they can just be absorbed by a nucleus, and that'll take the nucleus to an excited state. It can drop down, most likely through gamma decay, to its ground state. Or perhaps a little less likely, it can be enough energy to overcome the fission barrier, and it can undergo fission. So it's much more likely that it will undergo gamma decay if we create this excited state, but we could have fission. Rare. Now we're going to have a look at the Bright-Wigner equation for neutron capture. And if you remember a while ago now, in I think it was problem sheet 1, you had a look at some nucleus capturing a neutron, getting to an excited state. I think it was a thorium example. And then it could either kick out the neutron or it could undergo gamma decay. And you looked at the Bright-Wigner cross-section for this question. And you can write down your Bright-Wigner cross-section here as your spin factor g, pi. We usually write 1 over the momentum of the initial state particle squared. This could also be written in terms of lambda here, which is just the inverse of that. It's just the wavelength. And then we've got the partial decay rates of how it's formed and how it would decay. So most likely it's going to decay through the photon, and that's probably very close to the total decay rate here. How far away we are from the resonance energy of this excitation, and then we have to have this last bit here where we've got the total decay rate squared over 4. Now at resonance, this is quite simple. We've had a look at the Bright-Wigner cross-section close and on the resonance where this E minus E0, the term goes to 0, and this simplifies quite nicely, and we did this in problem sheet 1. Now, what about far, far away from the resonance? What if we've got very low energy neutrons, for example? How does this cross-section depend on the energy, for example, of the neutrons? Let's have a look at that. So far away from the resonance, this energy here is much, much smaller than E0. So this term E can just disappear, and we just have a factor of E0 squared here. Right. So this cross-section far below the resonance, we can just separate these. I shouldn't have done that. We can just separate these terms here into the stuff in the square brackets, which is basically a constant, and the stuff here to the left. This lambda value here is going to contain information about the momentum of the initial state particles in the central mass frame. So let's have a look at that. How does this lambda value go? Lambda is h bar over the momentum. So you can, the higher this is, or the higher the momentum is, the higher energy or the higher velocity neutrons that we have. If they're very low energy, they're not relativistic. So if they're very low energy, we can treat this classically. That's not a problem. So the higher momentum or the higher velocity we have here, the lower the the lower the cross section is going to be. We would actually expect the cross section to start quite high for low energy or low speed neutrons and fall away as their speed increases. So it actually falls away, this cross section, as 1 over the velocity of the neutrons. So this is 1 over v law. So let's have a look at this, right? Indeed, this is what happens. So for example, whether we're looking at helium capturing neutrons or boron, for example, the cross section here falls away as the energy of the neutron or the velocity of the neutron increases. And we can have a look at these, for example, the resonance that we're used to having a look at with the Breit-Wigner equation, but it means the cross section for neutron capture is only high for low energy neutrons. A nucleus is very unlikely to capture a high energy neutron. It has to be low energy. So we've got a bit of something to think about here between the sort of cross section for capture and having enough energy to overcome fission. So let's have a look here at uranium-235. If it can capture a neutron, it can go into an excited state, uranium-236 here, and undergo fission to 2 daughter particles. And these are inexcited states themselves. They usually produce in excited states. And what they'll do is they'll kick out some neutrons or photons as well to drop down into ground states. And they'll kick out these neutrons really, really quickly. Now, uranium-236, that energy is enough to overcome the fission barrier, and it's really, really good. We can use very, very low energy neutrons here to overcome that fission barrier. The fission barrier is very low. So we can make use of the high absorption cross section for a neutron capture and the fact that that's enough to get over the fission barrier. So uranium-235 is really, really good to use for just low energy neutron capture to undergo fission. Otherwise, we could have a look at a different isotope of uranium, uranium-238 here. If that undergoes neutron capture to uranium-239, we need to give the neutron a little bit more energy. The fission barrier for uranium-238 is or uranium-239 is 6 MeV. So that neutron has to give that 6 MeV roughly of energy. If we use a neutron of, if we use thermal neutrons of very, very, very low energy, we're not going to get thermal fission because the excitation energy of uranium-235 is only 5 MeV there. If we give that neutron just a little bit of energy, it can give enough energy to the excited state to be 6.4 MeV, and that'll overcome that fission barrier of 6 MeV. So we need to sometimes give those neutrons a little bit more energy to overcome the fission barrier in cases like uranium-238, but uranium-235 doesn't need them. So they're actually the more interesting isotope if we want to induce fission very rapidly, like in reactors. So uranium-235, we need to give it higher energy neutrons, which decreases the neutron capture cross-section. So it's a sort of a weighing up of two things there. Right, so when we induce fission in this way, the daughter particles, it doesn't matter what we're looking at here for uranium-235 or 238, the daughters tend to have the same neutron and proton composition, at least in ratios, as the parent. And they tend to be unequal in size. We did have a look at that earlier. The symmetric fission gives the highest energy output. However, the Coulomb barrier is highest, or the fission barrier is highest in those cases. So they tend to be unequal in size. So when we're creating these lighter particles, they have the same neutron to proton ratio as the parents. And back in the very early nuclear um, lecture, we had a look at the proton to neutron content of nuclei, and it tended to be pretty even for the light nuclei. But then when they got heavier, they they tended to have far more neutrons than protons. So when a heavy nucleus decays into a light one, they're too neutron rich. So what they do is they kick out neutrons very, very quickly, these daughter particles. They've got too many neutrons. So you can think about this as the asymmetry term in the semi-empirical mass formula. They kick out neutrons really, really quickly to try and get into a balance of protons and neutrons. They do this very quickly on the timescale of sort of 10 to the minus 16 seconds. And these are quite high energy neutrons as well. If we want to ever use them for uh, uh, fission again or inducing fission again, we need to actually slow them down. Now, they've kicked out some neutrons, but then they usually undergo further decay into more stable nuclei. For example, they will undergo beta decay to get to the most stable nucleus they can. And when they undergo beta decay, they again might have too many neutrons and kick out some more neutrons. So we've got two sets of neutrons coming out here. The first, when these fragments are first formed, when they're too neutron rich, will kick out some prompt neutrons in about 10 to the minus 16 seconds. And then we have to wait a little bit for this weak decay, the beta decay, and we might get some more neutrons coming out then. And these are our delayed neutrons, and they're quite rare. We get only about one delayed neutron for every 100 fissions, but they do come along later. Now, these daughter nuclei, I mean, when we induce fission, energy is released and we can use that to do some good work. But there's quite a wide variety that you can see. For example, from one of these uranium decays, there's quite a wide variety of nuclei that can be made. The fragments are unequal in size, but they can be different nuclei that are created. And some of them are actually useful for us, but some of them are quite nasty. So this is one of the problems. We have no control really over what is made, over what is useful to us, and over what we have to treat very carefully for the decay products. Now, we've got two sets of neutrons coming out. We've got the prompt neutrons and the delayed neutrons. But we can use these, hopefully, to be captured by other nuclei and induce more fission and have a wonderful chain reaction. So if we have if we have these fission producing daughter particles, and then we have our prompt and delayed neutrons, those neutrons can be used to induce others. And if we have one of those neutrons from a fission inducing a fission in another, we can have a chain reaction. And it depends about the rate of inducing another fission. So if on average we have the number of neutrons from one fission inducing fission in another, we'll have either subcritical, critical, or supercritical. So if it's exactly one, if one fission, a neutron from one fission induces exactly one other fission, then that's fantastic. If it induces more than one fission, then we're going to have a supercritical chain reaction, and that could be a problem. If it's fewer than one further induced fissions, then we have a subcritical reaction. Ideally, we want a critical reaction, exactly one further induced fission from each original fission. That gives us a wonderful steady energy release. And we'll have a look at what happens for supercritical chain reactions in a minute. Now, these prompt neutrons, as I said, they're the ones that come out first in 10 to the minus 16 seconds. They not only come out very quickly, they come out with quite high energies of around 2 MeV and are neutron capture cross-section, remember, it drops as 1 over V. So our neutron capture cross-section is actually quite low for these high energy prompt neutrons. We need to slow them down. We can slow them down to much lower energies, thermalize them essentially, and then they have very high neutron capture cross sections and can be useful for us and induce a chain reaction. So we need to slow them down. So this is what's done in fission reactions, and we'll go into a bit more detail in a second. Um, I usually say the nearest one to us right now, but I realize that you're all over the world right now, everybody. But the nearest nuclear reactor to Cambridge is Sizewell over in Suffolk on the coast there. And it uses the kinetic energy of the fission products from uranium to produce heat and electric power for the local area. There's two more types that you may or may not be aware of. There's research nuclear reactors as well, and there's a wonderful, beautiful one over at RAL called ISIS, and the neutron beams that are so that we have the undergoing of we're inducing fission, and we have lots of prompt neutrons being coming out, and those neutrons are used to probe the structure of matter in research. So the neutrons that come out are kicked out from fission. The prompt neutrons are really, really helpful there. And finally, we have breeder reactors. So this there's an example in Lanarkshire. There's Springfields up there, and that's converting typically non-fissile material into fissile materials that we can then use for power reactors, for example. So for example, if you take plutonium, if you want to make plutonium, it's very, very rare in the Earth's crust, but we can make it from uranium-238, which is quite relatively abundant in the Earth's crust. We can have neutron capture with uranium-238 to give us uranium-239. This can change via beta decay into neptunium and then decay down to plutonium. So this is how we can make plutonium, for example, from the more common uranium, and we can do the same thing from thorium-232 to make the more useful uranium-233. And then you can separate these from your materials chemically. So we can sometimes make the fuel for the power reactors using breeder reactors. Okay, next I'd like to talk about a very simple setup for a fission reactor. We've talked about what's happening in our fuel, and it really depends on what we're putting in there. We could have like natural uranium as we bring it out the ground is more rich in uranium-238, which needs quite a high fission activation energy. Uranium-235, if you remember, can get over the fission barrier with just thermal neutrons. So uranium-235 is really our target for the fuel here. Now, naturally occurring uranium as an isotope, it's at less than 1% of uranium. It's mostly uranium-238. We can use enriched uranium, which is about 2 or 3% of all uranium there. Or we could use plutonium, or we could use uranium-233, and we can make those in breeder reactors. So we're going to have some fuel in there that is going to capture neutrons and undergo fission. Right, the next thing we want to do is to try and moderate the neutrons that are coming out, slow them down so that they can induce other fissions, so that we can have a chain reaction. So we're going to put some material there that's going to slow down our neutrons, and it's going to do this by basically lots and lots of elastic collisions. We're going to need something that's going to transfer quite a lot of energy and slow down those neutrons quite quickly. We're going to need something with a light nucleus, nothing too heavy. Otherwise, there won't be much of an energy transfer. The lightest nucleus I can think of is hydrogen, and that's there very easily and cheaply in water. So we could have a water moderator, but the problem is with that a water moderator is water does like to absorb the neutrons as well as slow them down. So we could slow them down, but we're going to lose them. What we'll do is the hydrogen inside of our water will capture that neutron, and it will give us deuterium. It will give us heavy water. Not so useful. We want to keep our neutrons and not capture them. Okay, so let's think about using heavy water. So deuterium 2 with an oxygen atom, and we can get that from seawater. We can purify it there. However, we've got the same problem, is that we have the neutron capture. We'll have lots of fantastic elastic collisions that we want to slow down our neutrons, but it'll also capture the neutron, and instead of it'll sort of go through the same process here, and it will make tritium, which is a very highly radioactive and nasty product that we do not want. So maybe let's go to something a bit more safe that doesn't like to capture neutrons so much. Let's have a look at carbon-13. We can make this really cheaply in terms of graphite. Carbon is very available to us. It's cheap and easy. However, it's a larger mass nucleus. So we're going to need far more collisions to actually slow down our nucleus. So we won't have so much of an energy transfer. That will be quite low. So we're just going to have more carbon, essentially. So carbon is usually what we use here to slow down our neutrons that are coming out from the fission, those prompt neutrons from the uranium. The next thing that we want to do is take the heat that is produced, take the heat that's produced from our fission, make it to go and do some work. So it's going to get quite hot around here because of the fuel undergoing fission, and we're going to take that away to go and do some work. And we usually cool it, take the heat away to do some work using some gases like helium or carbon dioxide, or just very simply water. We also have liquid salt cooling systems as well, which is really interesting. But usually in the UK, we have gas-cooled uh, fission reactors. The final thing we want to do, we've got the fuel, we've got neutrons coming out the fuel to initiate other um, fissions. We're slowing them down to initiate other fissions, and we're carrying off the heat to do something cool with it. The next thing we want to do is try and control the reaction itself. So to control the number of fissions another one can induce. So we're going to control the criticality of our chain reaction. Try and keep it at k=1 at a critical chain reaction. We can do this using control rods, and these are usually made from cadmium, and they do like to absorb neutrons. So they're not slowing them down or anything like that. They're just going to absorb neutrons and prevent them from inducing other fissions. And so we're going to lower them in and out of our system to absorb neutrons as and when needed to control the rate of our chain reaction. Now, we have a little problem here, and that we can't really do this. We can't moderate our interaction on the timescale that we need. So natural uranium, as I said, is mostly uranium-238, and only a very small fraction of it is uranium-238, less than uranium-235, which is the one that we really want to try and induce fission in, less than 1% here. Now, if we have a look at the neutron capture cross sections for these two ones, the one that we're interested in, uranium-235, this is the one we want to induce fission in here. Its cross section drops away for neutron capture far more steeply than uranium-238. So the prompt neutrons that are coming out from the uranium-235 fission that we want to use to induce other fissions are quite high energy. We need to thermalize them away down to low energies, because if we keep them at quite high energies, they are going to get absorbed by uranium-238, and that's not useful to us. We're very unlikely to get over the fission activation energy there. So we want to slow them down, make it far more likely that they're captured by uranium-238. We're going to do that with our moderators. And we're going to control the number of them that we have to control the rate of the interaction with the control rods. Now, the problem is between one fission and the neutron inducing another fission is around 1 millisecond. And so if you remember, these control rods are huge. They need to be lowered in and out of our reactors. We can't do that on the time scale of a millisecond or milliseconds. This is going to take quite a long time. Even if we could do it on the order of seconds, we're not going to be able to control the interaction because of the rates that this is happening. So what happens if we can't control these neutrons? We can have a look at how the number of neutrons is going to increase with each fission here. So we're going to start with some number of neutrons at some particular time. And then we're going to have some increase in the number of neutrons. That depends on the small amount of time that we're looking at. The lifetime of the interaction, we've said, is about 1 millisecond between neutrons being produced and inducing another fission. And then it depends on the criticality of our reaction here, right? So if we've got k equals 1, then we're going to have an increase here of 0, because we're going to keep the number of neutrons around at a particular time as a constant. If we have a k of less than 1, then we're going to see a reduction in the overall number of neutrons. It's going to decrease. And if we have a k larger than 1, obviously our number of neutrons is going to start to increase, and I'll show you that it'll explode. So we can take this and have a look at what happens at some particular time, given what we had. We're starting with some number of neutrons, and that they should basically grow exponentially if k is larger than 1. Well, they should decrease exponentially if k is less than 1. So let's consider the mean cycle time between neutron production and inducing another fission as 1 millisecond. That example as we did before. How many neutrons are we going to have after just 1 second? So let's say we're going to have a supercritical chain reaction. Not a very supercritical one. I'm just going to say that it's 1% above 1. So the criticality is 1.01. That is supercritical. And let's have a look what happens. We are going to get an increase in our number of neutrons of e to the power of 10. So in 1 second, we will have 22,000 times more neutrons. And this is a very important reason why we need to control the criticality of our chain reaction. It really does explode if we cannot control it. A very tiny bit above 1, in 1 second, we will have 22,000 times more neutrons, inducing more fissions. So really what will happen is we'll have a huge amount of more fissions, 22,000 times more, and the chain reaction will go supercritical. It's going to heat up. The kinetic energy of the neutrons is going to increase. We won't be able to slow all of those down, and the fission cross-section will actually drop. Now, maybe that's a little not what you were expecting. Things will heat up, definitely. We will get very high temperatures inside our reactors, but we won't be able to slow down or thermalize the neutrons anymore. They will not be able to induce more fissions. So actually the chain reaction will drop away as it reaches some very high temperature. Your reactor's still at a very high temperature though, and you've got to do something about that. So it's stabilized itself. Because of the high energy of the neutrons, we're not inducing any more fissions, but you've got a very high energy, very high temperature reactor there, and this is what we call meltdown. So this is why we line these nuclear reactors with huge amounts of concrete, so that if there is a meltdown, we can contain that very high temperature material. So what's the solution to this? Because we can't control the number of neutrons on the timescale of a millisecond. What we could make use of is the delayed neutrons instead, and they come out at about 13 seconds later. They do take a lot longer to be produced from the fission products. So what we can do is design or redesign our original detector, and we will to make the baseline design subcritical to the prompt neutrons, so that we're always absorbing as enough of those neutrons using the moderators, using the control rods. We're absorbing those prompt neutrons so that it never gets to a critical or supercritical chain reaction. It's always subcritical. And then what we're going to do is use the delayed neutrons to take it to critical, so that we've got time to act. We've got time to move those control rods in. So we're going to get those fast prompt neutrons from fission, and we're going to remove them from the fissile material, and we're going to then slow them down, um, and drift enough of them back into the fuel to undergo fission. So we're really going to remove these away and get them to do some work and drift enough of them back in to give us a subcritical fission. And then we've got our delayed neutrons, which we can control on the time scale of 13 seconds easily with our control rods. And that gives us a nice critical chain reaction for thermal reactors. Okay, uh, now let's move on to fusion, from fission to fusion. So as a reminder, this is when light nuclei are fusing together into heavier nuclei, and this is energetically favorable. If you look at the semi-empirical mass formula, we are decreasing our surface term per nucleon, but we are increasing our Coulomb term, but the offset is enough to make this fusion favorable. So if you consider the most simplest process that we could do here, 2 protons to give us deuteron here, we need to overcome the Coulomb repulsion between these two like sign protons. The Coulomb barrier there is about 1.2 MeV between 2 protons, if they're about 1.2 femtometers away from each other. And the energy released in this interaction is 0.4 MeV. So that's a fusion barrier, for example, of about 0.8 MeV that it has to overcome. So how do we start to overcome these Coulomb barriers in order to fuse them together to get overall positive energy released? Now, it's quite easy to actually overcome the Coulomb barrier. These are only very light protons. We can do this very easily in accelerators. For example, the LHC, we're colliding protons. It's really easy to give them they're moving along with some energy, enough energy to overcome a fusion barrier and give you a deuteron. Easy, easy. However, we collide protons at accelerators, and they're very, very fine beams. They're very small amounts. We don't have high particle densities. So we can get fusion, but it's not actually at a useful rate because the particle densities are so low. You want to do this on a big scale. Actually, we have it already happening at a very large scale. We have this in the sun. So in the sun, we have a huge density of protons and neutrons as well as they're burnt up. We have about 10 to the 32 of them per meter cubed. Absolutely fine for the particle density there. We can use the sun, and we do use the sun to get useful amounts of energy. The way that fusion is done in the sun is that our 2 protons, for example, have enough energy to overcome the Coulomb barrier because of their kinetic energy. That's what should happen. So if you want to achieve this, to overcome this Coulomb barrier, you're going to need energies of, about 0.8 MeV or 1 MeV. Let's simplify it here. You're going to need energies of around 1 MeV, and that means the temperature has to be about 10 to the 10 Kelvin. But our sun is actually much cooler than that. It's only about 10 to the 7 Kelvin, 1,000 times cooler. And that means that our typical energies of our protons is only about 1 keV. They do not have enough energy to classically overcome that Coulomb barrier. So again, quantum mechanical tunneling is going to be required for fusion in the sun. So let's have a look. Our particle energy or our proton energy in the sun follows a Maxwell-Boltzmann velocity distribution. So these higher energy ones, they could even have enough energy to overcome the Coulomb barrier, but they'll have a higher probability for fusion with the tunneling because the barrier will be lower to them. And then the lower energy protons, they've got lower energy, the barrier will look quite high to them, so they'll have a lower probability for tunneling. So it all depends on the energy distribution or the velocity distribution of the protons in the sun, and we can use that to work out the rate of burning in the sun, the rate of this quantum mechanical tunneling for fusion. So what have we got here? We can use Fermi's golden rule here. Well, we did this back in chapter 2 to work out the decay rate or the fusion rate, and the rate of our process here. It depends on the cross section, which is a function of the velocity of our protons, the flux of protons that we have, and also the number density here as well of our protons. So we know the cross section is dominated by the probability for tunneling to happen, and we can use our gamma factor there that we had a look at originally for alpha decay. We're going to have an additional factor of 1 over v squared coming into the gamma factor from the 1 over p squared in the Bright-Wigner formula. Now we need to have a look at this decay rate over the average of the Maxwell-Boltzmann velocity distribution, and the average is going to sit at a much lower energy, but it's these ones in the tails that are quite interesting that will increase our probability here. So what we'll do is we'll integrate this decay rate over our Maxwell-Boltzmann distribution. We'll basically calculate that. We'll integrate this cross section multiplied by the velocity over the velocity range here. Now, what we find is that our fusion rate reaction rates peak at around 100 keV here. For all of these different fusions that we could consider here, they peak at about 100 keV, not the 1 MeV that we saw that we need to classically overcome that Coulomb barrier. And this is a temperature of around 10 to the 9 Kelvin. So the peak of these fusions is really happening from the protons in the tail of the velocity distribution. So if we consider these high energy protons that have about 100 keV of energy tunneling through to have fusion, we could consider the fusion of these 200 keV protons here to give us a deuteron and a positron and a neutrino. The cross section here is absolutely tiny. It's something like 10 to the minus 32 barns. It's a very, very weak cross section. So it's very, very unlikely that a particular proton is actually going to undergo fusion. But we have so many protons in the sun. Is it 10 to the 32 per meter cubed? The density of protons is so high. There's so many protons, even if the probability for that to happen is very low, there's enough of them burning. So each proton, for example, has a lifetime of around 10 to the 10 years before it actually does undergo fusion. So understanding the rates of these processes will define the burning rate in the sun. Our understanding of these nuclear fusion processes and their rates helps us to understand what's going on inside the sun. Okay, so let's have a look at the fusion processes in the sun. Even to take the most simple nucleus, which is just a single proton or hydrogen, and fuse it into the next heaviest element, which is helium-4, it's not just one simple process, it's actually a chain of processes. The first one here is the pp1 chain. Now, I just want to do a little bit of an aside here because we need to consider what nuclei we can actually form, what we can fuse together. So we have lots of protons around. So we've got a couple of protons here that we're going to fuse together into something. Why can't we fuse them into helium-2, which is basically a proton-proton bound state? What I'm going to try and argue to you here is that this cannot happen. So let's have a look, for example, at the only two nucleon bound state that we can have, and that's deuteron. We denote it with D, and that's a neutron proton bound state, and it has a spin of 1. That means that the neutron and proton here are actually in the same spin state. Okay. Now, we don't see a spin equals 0 state for deuteron. We don't see them with opposite spin. This is not seen. And we've seen, haven't we, from the spin-spin interactions, that actually the binding energy or the mass of the particle actually increases when we have the spins aligned. So we can maybe conclude that this spin equals 0 deuteron state is not observed because the binding energy is not large enough. So it's not seen because it's not bound together. Only the spin 1 state actually has enough energy to be bound together. So let's go and take this off to another two nucleon bound state, whether it's a proton and a proton bound state. We can have a look at the deuteron analogy that if they're both up, maybe we have enough binding energy, but if their spins are anti-aligned, we don't have enough energy. But if the spins are both in the same direction, this is forbidden because of Pauli's exclusion principle. They cannot both have the same quantum numbers. So whether this is a proton-proton or a neutron-neutron bound state, the simplest and only bound state of two nucleons is the deuteron. It's the only and that's the proton-neutron bound state. Right, so sorry about that aside. Let me just change back to the slides. It helps you understand what's happening here. So when we take two protons and we fuse them together, one of them has to undergo beta decay to change into a neutron to give us the bound state of a neutron, the deuteron, a proton and a neutron here. And it does that by changing into a neutron and giving us a positron and a neutrino here. And the energy released is quite small, as we said, it's about 0.4 MeV. Then another proton comes along and fuses together with that deuteron to give us helium-3, so two protons and one neutron. And then it drops into a lower energy state. It's produced with as an excited state, and it drops down by gamma radiation, and the energy release there is 5.5 MeV. So that photon is one of the photons, many of them, that come out from the sun and reach Earth. Now, finally, to create helium-4, we actually need two of these chains to happen, and two of these helium-3 nuclei to come together and fuse together into helium-4, and two protons are then kicked out and a photon. And the energy released there is huge, at almost 13 MeV. So if you wanted to take four protons and fuse just four protons together and change two of them into neutrons to give you helium-4. That would be the most simplest net reaction there. The energy released, even if we consider these two positrons actually annihilate with a couple of electrons nearby, the energy released is actually very small. We need this total cycle to actually happen, which, yes, includes more nucleons coming in, more protons coming in here to enable this cycle to happen. But the energy released is much, much larger. In total, in this cycle, we've got 26.7 MeV released, and that's about 6.5 MeV per proton that we're putting in. So the photons are coming out. They of course can undergo electromagnetic interactions with the matter in the sun. As they come out, the helium is staying there in the sun to undergo further fission. We'll talk about that in a minute. But the neutrinos are coming out here without any further interaction. Remember, they're really weakly interacting. Even though the sun is really dense and there's a lot of matter, it's very unlikely that they're actually going to interact there, and they'll come out pretty much unchanged. And that's quite cool because we can use those to probe the processes in the sun. The rest of the energy in terms of photons heats the core of the star back up, which enables us to do more fusion. So let's look at the sun. We can look at the sun and have a look at its luminosity, and it's about 10 to the 26 joules per second. And we can change that into MeV, for example, to compare to the energy that is given out per proton in this pp1 chain. So we've got 10 to the 26 joules per second. We convert that into MeV and we divide through by that 6.7 MeV to try and tell us how many protons are being burned up per second if we attribute the total luminosity from the sun to the pp1 chain. And that would be 10 to the 38 protons per second being burnt up in the pp1 chain. That's absolutely amazing. Huge number of protons. I mean, there's a huge proton density there, huge number of protons to burn, and about 10 to the 38 of them are being fused together into helium-4 every single second. Now, there's other further chains that are also possible here. There's the pp2 and the pp3 chain that I have here. So in the pp3 chain, we have helium-3 fusing with helium-4. So one of these helium-3s that can be produced in the pp1 chain might actually fuse, instead of with another helium-3, it might fuse with a helium-4 that was produced at the end of the pp1 chain. And then we'll get beryllium-7 and a photon that heats the core of the star. This will undergo beta decay. Sorry, this can capture an electron, undergo electron to capture, which is a type of beta decay, and change into lithium and a neutrino. And we can have a look at those neutrinos. And then the lithium can fuse together with another proton to give us a couple of helium-4s. So helium-4 is produced not just in the pp1 chain, but in the pp2 and pp3 chain here. And the pp3 chain here, again, we've got a similar start off as the pp1 chain. But instead, the beryllium-7 fuses together with a proton to give us beryllium-8, which then undergoes beta plus decay to give us, and then undergoes a fission to give us 2 helium-4 nuclei. So there's these 3 chains here, each of which are very important to fuse together protons and with the eventual final state of the helium-4, plus lots of neutrinos and photons and electrons and positrons. Now, there's also a rarer pp4 chain, which takes a helium-3 nucleus and a proton and fuses that together to a helium-4, but that's actually quite rare because of the Coulomb barrier that has to be overcome. There's even further ones. There's the carbon, nitrogen, and oxygen cycle as well. You can have a look at that if you want to. But these fusion chains become quite complex. So how on earth do we know this? How on earth do we know what's going on inside the sun? Most of these products are still hidden to us in the sun. We can't probe these photons. They will undergo more electromagnetic interactions. We can't probe the helium-4 as it's being produced, but what we can do is we can have a look at the neutrinos that come out of these processes. They are essentially unchanged. They're taking away only a small amount of the energy of these interactions. Most of it stays in the sun to heat up the core of the sun. They're taking away about 2% of the energy of the interactions. And we can then detect them as they reach Earth and see if they match the energy distribution and also the flux of what we were expecting. So, for example, we should be getting about 0.4 MeV neutrinos here, or up to 0.4 MeV. This is a 3-body decay. And then we should be getting some more neutrinos here from the pp2 chain and this 2-body decay here. So we've got some specific energies for that neutrino. And then we've got more neutrinos coming from the pp3 chain here. So we can have a look at our neutrinos from the sun and see if the flux and the energies correlate to what we're actually expecting from these fusion processes in the sun. So we've got lots of experiments that have had a look at these solar neutrinos. Super K looked at the high energy neutrino spectrum, and then we've had chlorine and gallium experiments that have had a look at the lower energy neutrino spectrum. It's harder to see lower energy neutrinos, of course. So we've got a distribution from the neutrinos coming from the pp chain. So that's this neutrino here, and it should end at about 0.4 MeV. We should have that typical 3-body decay energy spectrum there from our neutrino from the pp1 chain. We've got a couple of specific energies coming from our pp2 chain, where we've got that 2-body decay into beryllium, from beryllium-7 into either an excited state of lithium or the ground state of lithium. And then we've got the neutrinos from the PEP, that very rare PP4 chain there, and then we've got uh, our three body decay energy spectrum from the beryllium 8 decay there. So we can compare the fluxes that we detect from the sun, from the neutrinos from the sun. We can compare the energy distributions and see if our understanding of the fusion processes in the sun that's encapsulated in the standard solar model is actually correct. So, do we understand the temperature of the sun and how that changes from the core all the way to the outside of the sun? So, how does the composition of the sun change with radius? How does the density of it change? And how does the temperature of it change? And we need to test that we understand our nuclear cross sections as well as the composition of the sun. So the sun, the neutrinos from the sun, the solar neutrinos are actually very interesting for probing all of these things. And this is why scientists went to go and measure them, and they found a problem. The neutrinos from the sun should be electron neutrinos. They are coming from usually beta decay or electron capture, so they should be of the electron flavor. And interestingly, we saw that the flux of these neutrinos of the electron flavor was only about a third of what was expected. And this was the solar neutrino problem. So I'm linking something here now back to the particle part of the course, the neutrino oscillations. So this was one of the first, as well as the atmospheric neutrinos that we discussed as part of the neutrino oscillations, the solar neutrinos were also a problem. And it was relatively recently solved by the SNO collaboration. That's the Sudbury Neutrino Observatory. They reported that in the the neutrinos coming from the sun, there was a significant non-electron neutrino component. They weren't just electron neutrinos. This is telling us that they were originally created with electron flavor, and they oscillated into muon or tau flavors. So snow was this absolutely massive vessel of heavy water, 1,000 tons of heavy water, nice and cheap, a huge volume to try and detect those very, very rare interactions of neutrino with the nuclei there. So a neutrino would come in and it would interact very weakly via the weak force with the nucleons. The nuclei inside the heavy water. So basically the deuteron there. So the neutrino would come in and it would change one of the it would change the neutron in the deuteron here into a proton. And then to conserve lepton number, of course, an electron will come out. So what this electron neutrino is doing is exchanging a W boson with one of the d quarks in the neutron, in the deuteron here, and changing it into a proton. As it exchanges that W boson, it changes into an electron. So the idea was to study the neutrinos that are coming in particular from the boron 8 decay. So targeting a particular energy range that was suitable for this detector material. And then the electron could be detected via the Cherenkov radiation. So there's lots of PMTs inside there. So what you would expect is that the electron neutrino here would produce electrons, the muon neutrino muons, exactly. So they're measuring the electron neutrino flux using this electron final state, where we have the exchange of the W boson. But there's other weak interactions that can happen. There's the weak neutral current that can happen as well. So any neutrino of any flavor can come in and exchange a Z boson with the quarks inside of this deuteron. The neutrino itself is unchanged. We're not going to produce a charged lepton in the final state. And the deuteron basically breaks up and we detect the proton and the neutron rather than any electron. And then finally, we can have other neutral current interactions here where any particular favor of neutrinos comes in and exchanges a Z boson with the electrons in this heavy water. And it'll basically exchange some momentum and energy via the exchange of this Z boson, and you can detect that electron. and you won't detect the protons. So this is a very different one. So you've got our neutral current interactions here that will tell us about the total flux for all of the neutrinos. So it doesn't care if that it's an electron neutrino. And we can detect the electron flux specifically by using the charged current weak interaction. Now, while we did see a reduction in the electron neutrino flux from the sun, as expected, it's about a third of what it should be, we saw that the total flux was absolutely as agreed. So what had happened is the electron neutrinos had oscillated into other flavors. And this was evidence for the solar neutrinos undergoing flavor oscillations at about, well, certainly above this now, but at a 5 sigma, a discovery level. So neutrinos from the sun are very important. They allow us to probe the fusion processes in the sun, but further fusion processes do occur in stars. Not quite yet in our sun, but they have obviously occurred in other stars, and they've given us the heavier elements that we see around us today. So starting off, just to burn together protons or hydrogen into helium, at some point the hydrogen is going to run out, and the star will stop burning so much, and there will be less of an outward pressure from the burning of the hydrogen, and instead the gravitational forces will start to take over, and the star will undergo gravitational collapse. As it does that, it will start to squeeze all of that material into a smaller and smaller volume, and the temperature will rise. And in fact, the temperature will rise until it becomes hot enough to burn together um, larger nuclei. For example, helium-4 to create beryllium-8, or carbon-12, or oxygen-16. And then the outward pressure will start to increase, and the star will stabilize until that fuel's run out, and it will undergo further gravitational collapse, heat everything up, and have further fusions, and there'll be this cycle of gravitational collapse and more fusions to heavier and heavier nuclei. So this is always actually I've always loved this. This is actually quite cool on the lifetime of a star, and how these heavier elements are actually created from the increase in energy that we have from the gravitational collapse of the stars. And this will happen until we reach the most tightly bound nuclei. If you remember, the fusion is going to happen or be energetically favorable up until we reach that broad maximum of the binding energy per nucleons. And that happens at around iron and cobalt and nickel, and it will basically stop there. We won't have any more fusion. In fact, if you want to create the much heavier elements, this has to be done using a supernova. You have to put energy into the interaction. So we have these very high energy supernova explosions that will, for example, take iron here, and iron will capture more and more neutrons here to become a heavier and heavier isotope. And then it will undergo beta decay to cobalt 59. And these very complex processes need energy being put into the reaction, which is what we get from supernova explosions. So the heavier elements are rarer simply because they come from these very rare supernova explosions, and all of the lighter ones from iron will come from the regular gravitational collapse and increased temperature of a collapsing star. Now, nuclear processes are really important to understand what was going on back in the very early universe as well. In the very early universe, just after the Big Bang, we had protons and neutrons that had formed from our initial quarks. They had come together to bound states there. And this happened when but then as the temperature fell sort of below 10 to the 9 Kelvin, the protons and neutrons would bind together into more complex nuclei like deuterons, like tritium and helium. And the rates that these happen, that those typical reactions actually happened, is a very sensitive is very important as the evolution of our universe. As the temperature of the universe evolved, as time went on, the rates of these interactions would change. And at some point, they would freeze out and give us the abundances of the like nuclei that we see in the universe today. So what we've done is we've taken the WMAP experiment, which looked at the cosmic microwave background radiation, and this would tell us about the density of matter relative to photons, so the matter and radiation dominance of the universe. And we could also have a look at the abundance of these particular nuclei, like lithium and helium and deuterium and helium 4 here, relative to hydrogen as well. And that tells us basically how these developed, how hot deuteron, tritium, and helium 3 and 4 actually developed in the universe, giving us the abundances that we see today. It's a very, very sensitive test of the Big Bang model. Now, in particular, what happens is that some of these processes freeze out when the temperature becomes too low. For example, protons interacting with antineutrinos here will change into neutrons and positrons. And then neutrons can change back into protons as well. Now, the energy of these interactions is different. So a proton changing into a heavier neutron needs an input of energy from this neutrino. But with this neutron, for example, can take quite a low energy neutrino here to change into the lighter proton. Now, this is quite important. As the energy of these neutrinos dropped with the temperature of the universe, as the temperature, as the universe went on in time, the temperature dropped, the energy of the neutrinos dropped. This interaction would freeze out. It could not happen. But the neutron interaction, for example, could carry on and happen. And this freeze out depends on the temperature and also the density of the matter in the universe. So that'll control the rate of these interactions. And it also depends on how many neutrinos, of course, we have here to initiate these weak interactions. So we can probe how many neutrinos were around in the early universe to give us these proton to neutron and neutron to proton reactions, which in turn, of course, affect the abundance of deuterons and tritium and helium 3 and 4 in our universe relative to hydrogen. Now, more usefully, what we'd like to do is use fusion to do some work. And we've been doing fusion in the lab for almost 100 years now. And it was done, I'd love to say it's here, it was done for the first time, or at least demonstrated for the first time, here at Cambridge at the Cavendish Laboratory. This was done in 1932 by Oliphant here. So what we need to do to create fusion is we need some high energy, some high temperatures, and some very controlled conditions. As I said, we can fuse protons together very easily with particle accelerators. But to do this usefully in large amounts to make use of this energy, we need high density of fuel or protons essentially, and high temperatures, and we need to control it. So we've been doing this for a while, and the big challenge is to try and get a useful amount of energy out, more than we're putting in. At the moment, we haven't reached that point, of course. This is a challenge that maybe you'd like to do. We haven't reached that point yet, but we would like to, so that we can, like fission, we can put this to use and generate some clean energy. So let's have a look what we could use here. We could take two deuterons, we'll just get that from heavy water, in seawater, for example, fuse those together to give us helium 3, and a neutron would be kicked out there. Now, we would release about 3.3 MeV in energy in that interaction. If instead we create tritium 3, that's a hydrogen with two neutrons and one proton here. So we'd kick out a proton here. We'd release a little bit more energy, 4 MeV. Instead, if we fuse together a deuteron with tritium to give us helium 4, just like it's done in the sun, for example, we release a huge amount of energy, 17 MeV, and this one's particularly attractive to us. This is called the DT, the deuteron tritium fusion reaction. It gives us a huge energy release. Out of all these very simple fusion processes, there's a huge release there. We like that. And it also has the lowest Coulomb barrier out of all of these. Now, unfortunately, most of the energy is released in that neutron, which doesn't help actually to heat any plasma that we're using here. And so that's yet less useful to put that to work. And also tritium that we're using in the initial fusion is really, really unstable. It's got a half-life of around 12 years, and it's really quite nasty to make and produce. We could, though, take lithium and get it to undergo neutron capture to give us helium 4 and tritium, and then maybe use some of those additional neutrons to heat up or kick off the neutron react the fusion reaction. So maybe we can make it from lithium, which is a bit easier to deal with. So what do we need? The first thing you need to do is get your nuclei. So you're going to need to ionize the electrons away from atoms to give us just a nucleus. And this is going to create, you're going to need to basically create a plasma of all of our nuclei. So we're going to ionize our atoms, strip away all of the electrons to leave us with just the nuclei. And we're going to need energies of around 10 keV to do that. So temperatures of around 10 to the 8th Kelvin. Um, we can do this quite easily. We can heat it up by applying some radio frequency energy and heating up our plasma to get it to higher and higher temperatures to try and get those nuclei to fuse. Now, if the process is self-sustaining, that we get basically heating from our helium, our alpha particles, exceeds the losses that we're going to get from just simple radiation from photons. So we get Bremsstrahlung, for example, leaking away the energy from our plasma. But if the heating that comes back into it from our helium-4 nuclei exceeds those losses, then we can declare ignition. And we've been able to do that. But what we haven't been able to do is to break even. So that this it's not just about the heating of the plasma. There's more power out than we're actually putting in, including all of these losses, for example, from Bremsstrahlung. So for this, we're going to need to understand the fusion rate, the rate of energy, the energy loss, and we're going to need to break even when we get this generation of energy to be larger than everything that we're putting in there. So commonly people look at the triple product for this. We're interested in the density of our material, so we need lots of high density of fusion fuel. We need a long lifetime. We need this to be undergoing fusion for a long time so that we can make useful amounts of energy, and we also need to keep the temperatures quite high as well. So how do we do controlled fusion? How do we control a plasma? Really, there's two ways. There's inertial confinement and magnetic field confinement. You may be less familiar with the inertial confinement, but basically we can use very high energy laser beams to zap a pellet of fuel and confine it to a single space. And that will heat it up as well, and that will keep it still. Now, the problem is that these are very tiny pellets. It works quite well, but these are very tiny pellets, and at some point they will have all undergone fusion there, and your fuel will have been depleted. And you need to stop your experiment and replace your fuel. So the lifetime of the fusion production there isn't very useful to us. Instead, what we could do is build something on a huge scale and have a huge plasma that we can control in a magnetic field. And the most common shape for these containers is a donut, i.e. a tokamak. And the magnetic field here will keep it away from the walls of our container. And this has been used for a very long time now because the magnetic field that we need to apply is relatively simple. But other shapes for the magnetic confinement are being explored and used more commonly now, since we can control magnetic fields over very small spaces and over very short timescales. So we might be moving away from tokamaks, maybe spherical vessels or something a little bit more complicated, to improve our triple point product. So one of the most successful, historically anyway, the most successful fusion experiments is the Joint European Torus Jet, and that's over at RAL, and that's been doing really well. For getting us some really high plasma densities over long lifetimes, but it can't do that simultaneously. So it's been able to get long lifetime plasmas, but not with the high enough density to really make this useful, or high enough densities with a short lifetime. So we're yet to break even with JET. Then we've got the National Ignition Facility over in the US. They've broken even, but they haven't yet achieved ignition. So that's when, remember, the heating from the alpha particles, or the helium-4 basically coming out from the fusion, is enough to exceed the Bremsstrahlung losses from your plasma. And then finally, and I've been saying this for a long time, we have ITER, which is always about 20 years off of the horizon. It's been built, and they're trying to, the design there is to break even. But this is very much a learning process. We haven't done this in the lab yet. We're still about 20 years away, we think, from breaking even with ITER. This is very much a long running experiment. I've been saying this for a long time. So if we can get ITER to break even, if we can understand a controlled and useful fusion in the lab, this will probably be done with ITER, and it will probably be about 20 to 30 years before we can make that then commercially viable. So if you want to get into something that can really change the world for some wonderful clean energy generation, it could be fusion. This could be your work, either understanding nuclear processes from a theoretical side, or by building and designing these experiments to achieve a breaking even fusion process in the lab. Okay, so this is the summary slide for chapter 16, and the last summary slide for the course. So we started off by looking at fission, in particular spontaneous fission. That's possible for lots of nuclei, but usually it's very rare because there's a fission activation barrier, because the Coulomb, the surface term increases there. And what they usually do is undergo alpha decay or beta decay first. So the natural spontaneous fission is actually quite rare, but a few do it, and they need to tunnel through that fission barrier. We can help it along by giving a nucleus a low energy, a thermal neutron, which could take it to an excited energy that will be enough to overcome the fission barrier. So this neutron absorption there and the cross sections and understanding that is really important. And this is what we use to induce fission in the nuclear reactors and also in bombs. We've seen that they usually undergo an asymmetric fission because symmetric fission gives the largest energy release, but it also comes with the largest fission barrier. So asymmetric fission is the norm. And along the way, for those decay products, lots of neutrons are liberated as they get rid of neutrons. They don't need to be as neutron rich as the parent. Now, the chain reaction is really important because we can use those neutrons to induce other fissions. Controlling that is ever so important. The prompt neutrons are difficult to control on the timescales of a sort of 1 millisecond. They're released so quickly and they induce another fission so quickly, even when, so we need to, we usually take those out of the equation, thermalize them and feed them in as necessary, design a nuclear reactor to be subcritical to those neutrons, and instead use the delayed neutrons that come after beta decays on a longer lifetime of sort of 10 seconds or so. And then finally, we've been looking at fusion, which again is a tunneling problem because we have to overcome the Coulomb barrier. We're trying to get, for example, two protons to fuse together. To do this, we need high energies or high temperatures, which is present in the sun. So there's fusion processes in the sun, despite only, again, it's a tunneling problem because despite they're not actually at the energy we need to overcome the Coulomb barrier, but they can tunnel through them. And this led us to probe the fusion processes in the sun using solar neutrinos. And then we saw that deficit in the solar neutrinos, and it led us to understand neutrino oscillations. And nuclear fusion is also very important for nucleosynthesis, i.e. how our light nuclei were made in the very early universe. It's a very sensitive test of the Big Bang. And then finally, on a more practical scale, on a more practical note, we want to have controlled fusion. And this is a very, very hot topic and somewhere which I hope that some of you will be able to contribute here. We have yet to achieve a controlled fusion in the lab which generates more energy that we put in. We have yet to break even. And this is a very interesting problem that needs people like you to work on this. So that brings me to the end of the lecture course. We've gone through particle physics and we've gone through nuclear physics here, and I'll be setting up some some sort of office hours on Google Meet, I think, so that we can chat and you can tell me about any questions that you have, and we can work through any problems as we usually do at the end of lectures. So I thank you very much for being a great class, and thank you very much for staying with me throughout these very weird times and a very odd way of lecturing. And I wish you best for the summer, and I hope to see you all again back at Cambridge next year. Bye bye.